Hello students, in today's lecture we will be continuing with function and we will be discussing about types of the function, composite function, inverse, even odd and at last about the periodic function. So let's list down the points we are going to cover in today's lecture under the head functions. So we will be talking about first types, that is one, many one, onto and into. Then we will be discussing about composite function. After that we will take inverse, then even odd function, at last about periodic function. So these are the points we are going to take in today's lecture. So let's start with the first one, that is types. Types of the function. So first we will be talking about one, also called injective function. One function, how we describe it? As in case of function, we define that every element of set A should have single image in set B. Right? So we have given the condition on set A. Now let's talk about the set B. If I say that every element of set A has one pre-image, whichever is related. I repeat, suppose there are 10 elements in set B and only 8 are related to some elements of set A. Then these 8 elements should have one pre-image in set A. Right? So let's list it down. Through Venn diagram, we can say this is called one function. Every element of set A, whichever related, has just one pre-image in set A. Now there are 4 elements in set B, but only 3 has pre-images. But every element which has pre-image has just one pre-image. It is not 2 or more than 2. So again, this will be one function. So these are the two types we can describe for one. But instead, if I describe it like this, A, B, C, D, E, M. This function is not one because E has 2 pre-images. This function is termed as many one. Again, this one will be termed as many one. So these are the two examples for one. This is one. This is one. Right? This one, third is many one. Similarly, the fourth one is many one. Correct? Now let's put it in terms of equation. How we check it? Fx1 equals fx2 implies that x1 equals x2 only. Then f is called one function. Otherwise, it is called many-one function. Right? So fx1 equals fx2. It implies that x1 equals x2 only. Then we say the function is 1, 1. Otherwise, we term it as many-one. This is one method to define 1, 1 or many-one. Let's take another way. If suppose f is strictly increasing or strictly decreasing in its domain. If f is strictly increasing or strictly decreasing throughout its domain, then the function is called 1, 1, otherwise it is many-one. Then it is 1, 1. Right? When I say otherwise many-one, there is one exception, we have to take that out. And what's that? If f is increasing only or decreasing only in its domain, then it is 1, 1, otherwise many-one. What's the difference between the two? When I say it is strictly increasing, meaning f dash x is positive, then definitely it is 1, 1. When I say simply increasing, then I'm using the term f dash x is greater than equal to 0. Correct? Now, if this equality is for a moment, means just for a point, then we say the function is 1, 1. But if it is in an interval, then it will not be 1, 1. Meaning that if the function goes like this one, its derivative will be 0 at origin. This is clear. At this point, the derivative will simply be 0. Origin. But the function is increasing function and the function is 1, 1 as well. Instead, if I draw the graph like this and it becomes constant for some interval and then again it is increasing. So again the function is increasing but not 1, 1. So when I'm using the term equality in derivative, I'm mentioning here that it's for the point. It is point-wise. So if it is for some interval, then it will not be 1, 1. In that case, it will be termed as many-one. This is clear? So this is alternative approach for checking out 1, 1. The simple way for saying the term 1, 1 is when you draw a line parallel to x-axis, it's cutting the curve just at one point everywhere. But if you see it is touching for more than 1 point, like for this entire interval, then the function will not be 1, 1. If we draw the function like this, here it is cutting at 1 point, but at some time we see that it is cutting at 3 points. So the function is again not 1, 1. This is simply many-one. Right? So please ensure, the important point is when you are drawing a line parallel to x-axis, it is cutting just at 1 point or touching at 1 point. So we say that the function is 1, 1, otherwise it becomes many-one. So equality can also be included with the derivative part if it is for points wise only, it is not for some interval. Correct? Okay, let's talk about onto and into functions. Okay, let's talk about onto function, also called surjective function. if entire codomain is the range of the function, meaning there is no element in set B which is unassociated, which is not associated with any element of set A, then we call the function as onto, meaning that if we draw Venn diagram again, we have seen that this function was 1, 1. Now I will say this is onto as well. This function is 1, 1 onto. Similarly, if I write ABC here, DEMN here, and I relate in this manner, we have seen this function is also 1, 1, but it is not onto and it is called into function, right? What we have said for onto, entire codomain is the range. Here no unassociated element is there in set B, but in this case there is one element n which has no pre-image. So this function is not onto and it is called into. This function was not 1, 1, we called it as many 1, and this is also not onto because there is one unassociated element, so this is into. Now this function is not 1, 1, it is many 1. And clearly this function is onto because there is no extra element in set B. So we can see here 4 examples for onto and into. Correct? So in this manner we define onto or into. So we can write it in terms of equation. If FA equals B, let us say the function is defined as f from A to B. As I am doing f from A to B. If FA equals B, FA meaning range, B meaning codomain, then F is called onto, otherwise into. We have given 2 different names to 1, 1 as well as onto. For 1, 1 we have said injective, for onto we have used the term surjective. Now if the function is 1, 1 onto, it is also called bijective. Known to you? Right. So 1, 1 onto, it is also termed as bijective function. This point is clear? Okay. Let us take some examples to understand 1, 1 onto, many 1 into. Let f is defined from 0 to infinity to 0 to infinity given by fx equals x upon 1 plus x. And I have to check whether this function is 1, 1, many 1, into, onto. For 1, 1, let us say we write fx1 equals fx2. When I am saying fx1 equals fx2, I use here x1, x2 as algebraic terms, not the numerical values. Because if the function is 1, 1, you will never get 1 equals to 2. So you will get some not acceptable results in that case. So it's better to go with the algebraic terms. x1 upon 1 plus x1 equals x2 upon 1 plus x2. Simplifying, we get x1 equals x2. Clearly the function is 1, 1. Right? Okay. If I consider the function x upon 1 plus x without looking at this part, then I can say the domain of this function is all real numbers except minus 1. If f from a to b, a is given the actual domain, then obviously the range will be the actual range. Then I can find range by saying this is equal to y and find x in terms of y, but it is not given here. Here it is given the domain is just 0 to infinity, right? The smaller part of the actual domain, what could have been for this function. So obviously the range may also change. So how we go for the range of this function? Since the function is 1, 1, best choice is 1, 1 meaning increasing or decreasing only, right? Meaning that the function will take maximum and minimum value at the extreme points. See, the function goes in this manner. So minimum is going at the first point and maximum is going at the last point. If the function goes in this manner, minimum is going at the last point and maximum is going at the first point. So there is no problem. Just check for the extreme points. So here we see f of 0 is 0, and as x approaches to infinity, f approaches to, we can divide by x. So we find that it is approaching to 1. Therefore, range of the function comes out as 0 to 1 open at 1. That is clear. So now we have the range of this function as 0 to 1, while codomain was given to me 0 to infinity. So we can see that range is not equal to codomain, hence f is not on 2. So we can say the function is 1, 1 but not on 2, or we can say f is 1, 1 in 2. That point is clear. Take another example to understand. Note it down. What we have done here, we have simply used the approach fx1 equals fx2 to check out 1, 1 and hence obtained range using the fact that since the function is 1, 1, so it will take maximum and minimum at extreme points at the last points, end points of the interval. This is clear. Let's go for the next one. Okay, let's take the next example. Suppose the same function is taken this way, f from r minus minus 1 to r minus 1. Now, the function is given same one, that is fx equals x upon 1 plus x. Right? We have seen in the last example this function is 1, 1 and we nowhere use the fact that what is the domain, right? Because when we said x1 equals x2, when we went with fx1 equals fx2, we obtained x1 equals x2. Let's write this thing again. fx1 equals fx2, implying that x1 upon 1 plus x1 equals x2 upon 1 plus x2, which on simplification gave us x1 equals x2, right? Now next part. Here the range of the function has changed because the domain is r minus minus 1, correct? Again you can say since the function is 1, 1, you can plan for the extreme points, but there is one problem and that is minus 1 is excluded. We can go other way around, like saying y plus yx is equal to x, giving me x equals y upon 1 minus y. So we can see range of the function is all real numbers except minus 1, same as the given one. So here we observe that f is bijective. Here it is 1, 1 as well as on 2. This is clear. Take the next one. F from R to R given by fx equals 3x plus cos x. Now here the function involves algebraic as well as trigonometric term. If I go with the approach fx1 equals fx2, I will not be able to conclude it direct comfortably. Here what we do is, we say let's find the derivative. It is 3 minus sine x. Correct? Now the function sine x takes value between minus 1 to 1. So 3 minus sine x, we can find it. Sine x is taking values between minus 1 and 1. So obviously minus sine x is also lying between minus 1 and 1, giving me 3 minus sine x adding 3 on each side, it is lying between 2 and 4. Correct? Now, what we see here, that f dash x is equal to 3 minus sine x, correct? Which is lying between 2 to 4. Right? So, we can clearly say that this function f dash x, since it is between 2 and 4, so we can say that f dash x is always positive. The function is always positive, giving me the conclusion that the derivative is always positive, meaning that function is strictly increasing. When this function is strictly increasing, we can say f is 1, 1, meaning that f is 1, 1. First job is clear, the function is 1, 1. Now, the function is given r to r. When x is approaching to minus infinity, this term is approaching to minus infinity, plus something between minus 1 and 1. So we can see the minimum value of this function is also going to minus infinity and the maximum is going to plus infinity. So range of this function is r. Therefore, f is 1, 1 on 2. This is clear? Take another one. Fx is given by e to the power minus x square, e to the power x square, divided by e to the power minus x square plus e to the power x square, and f is defined from r to r. Now, when you find that the term x square is involved throughout the function, there is no linear term x. Right? When no linear term x is there, so whether you put a or minus a, because r has plus as well as minus values, right? So when you write here plus a or minus a, you can see the function is going to assume same value. When you put 1 or minus 1, x square makes it 1, so you are getting the same value. Clearly, f is not 1, 1. As it assumes same value for x equals plus minus a, where a is any real number. Right? So we find that the function is not 1, 1. Let's talk about the range of this function. Fx is given to me e to the power minus x square minus e to the power x square divided by e to the power minus x square plus e to the power x square. Correct? Now, if I divide numerator and denominator by e raised to the power x square, I see it as this one. As x approaches to plus infinity or minus infinity, it will be going for the same value. F is going to take value e to the power minus infinity goes to 0. So 0 minus 1 upon 0 plus 1, that is minus 1. Correct? Now, as x is going to 0, what we find? We can put the value equality as well. We observe that f of 0 becomes e to the power 0, that is 1 minus 1 upon 1 plus 1. So it is simply 0. So we find range of the function as -1 to 0 approaching towards -1. We find the value range as -1 to 0 where -1 is open and 0 is closed, that is included. I repeat this question. Here it was given fx is e to the power minus x square minus e to the power x square divided by e to the power minus x square plus e to the power x square. Only even powers for x. X domain is having positive as well as negative values. So it clearly meaning that the function is not 1, 1. First point is clear. Now for range, when I observed x is only involving square terms, meaning the function is even function, so it is symmetric about y-axis. So whatever value it is going to take on the right side, in the similar manner it will be moving for the left side. Correct? So it is sufficient to check for 0 to infinity part only. We will automatically get for minus infinity to 0 part. I said when it is moving to plus infinity or minus infinity, either way it will be going for -1. And at 0 it is taking value 0. So we got the range. This is clear? Okay, let's go for the next one. Okay, let's take the next example. Let f from R to R be given by fx equals x cube plus x square plus ax plus 4 be bijective function. Find a. Now a polynomial is given x cube plus x square plus ax plus 4. It is given this function is bijective, meaning 1, 1 as well as onto. Correct? Now the function is 1, 1 onto. So how we go for this kind of questions? Fx is given to me x cube plus x square plus ax plus 4. Let's find the derivative. F dash x is 3x square plus 2x plus a. Now it is given that function f is bijective, meaning 1, 1 onto. Correct? Function is 1, 1. So f dash x is either greater than equal to 0 or less than equal to 0. Now quadratic, we are looking for either only positive term or only negative term. Coefficient of x square is positive, so it cannot be only negative. So we need to say it is greater than equal to 0. Quadratic expression is always positive, say greater than 0 only. When it is there, it is the case when discriminant is negative and coefficient of x square is positive. Equality is also included, so let's say d is less than equal to 0 and coefficient of x square should be positive, which is already there. So we are looking for the discriminant now. This gives me 4 minus 4 into 3 into a less than equal to 0, giving me a is greater than equal to 1 by 3, or we can say a belongs to 1 by 3 to infinity. Correct? So function becomes 1, 1. Onto will always be there because we are saying fx is polynomial. Correct? The function, we are saying that the derivative is always greater than equal to 0, means the function will go now in this manner. Correct? So we can see the minimum is approaching to minus infinity, maximum is approaching to plus infinity. Function becomes 1, 1 onto for the range for a as 1 by 3 to infinity. This point is clear. Let's go for the next one. Let f from n to z given by fx equals minus x by 2 when x is even and x minus 1 by 2 when x is odd. Correct? Fx is minus x by 2 when x is even, x minus 1 by 2 when x is odd. Here we can see that if x1, x2 both are even, the function goes minus x1 by 2 minus x2 by 2, that is x1 equals x2, so it looks like 1 1 function. If x1, x2 are odd, then we say again x1 equals x2, again it looks like 1 1. If I consider one of the two is even and other is odd, one is even, other is odd, what happens? Minus x1 by 2 equals x2 minus 1 by 2. Correct? That is, we find x1 plus x2 is equal to 1, which is not possible. Why? Because x1, x2 are from the domain, one is even, other is odd, and the sum of the two is coming out as 1, which is not possible, sum of two natural numbers. So we see here that the third case cannot be taken. Now only two cases are there, first and 2. From these two we can clearly see the function is 1 1. Now let's talk about the range of this function. When x is even, on substituting values as 2, 4, 6, 8, we find when we say x is 2, we get minus 1, 4 we get minus 2, etc. So we are looking here, negative integers are obtained when x is even. Similarly, when x is odd, we find fx as 0, 1, 2, 3 and so on. Combining the two, we see that all integers are covered. Therefore, we can clearly see the function is onto. So range of the function comes as set of integers. Therefore, the function is onto. Function is 1 1 as well as onto, that is the given function is bijective. This is clear? Okay, let's go for the next one.